Hi, I'm Andreas, and welcome to this presentation for Lutsig, a Verified Verilog Compiler for verified circuit development. Let's start by summarizing what is going on here. So first, it is good to know that Verilog is the most widely used hardware description language today. And what we have done is that we have built a new Verified Verilog Compiler called Lutsig. And Lutsig targets a class of FPGAs, that is, programmable logic, and specifically, Lutsig is capable of producing technology map netlists for FPGAs. And in the paper and in this presentation, we show how to use Lutsig in verified circuit development. And lastly, all of this has been done inside the interactive theorem prover Hall 4. To use Lutsig in verified circuit development, we suggest following the approach usually taken inside ITPs when developing verified software. Concretely, you start with a Verilog design, and then you use Lutsig to produce an FPGA netlist. After this, you prove your circuit correctness theorem on the source level. You do this on the source level because it's easier to reason on the source level than on the target level. But we are ultimately interested in a target level correctness theorem, and to get this from our source level correctness theorem, we compose the source level correctness theorem with Lutzig's correctness theorem to get the target level correctness theorem. To be able to prove the correctness of Lutzig, we need a formal semantics for both the source language and target language, so let's look into those. For the source language, that is Verilog, we base our semantics on earlier work, and the semantics is a function operational semantics, which is supposed to be a sound simplification of the latest Verilog standard. And for the netlist language, the semantics there is also a function operational semantics, and the netlist is represented in a linear fashion. This is easier to work with than a netlist represented as a graph. And our main design goal for the netlist language was simply to have a language that is easily pretty-printed for communication with PNR tools. Let's also say something about the internals of the compiler itself. So I will mention 4 important passes here, and let's go through them one by one. So for the Verilog to netlist compiler, the compilation algorithm here is based on the compilation algorithm from the unverified Verilog compiler CSYN. If you're familiar with conventional software compilers, many parts of Lutsig will look familiar to you. What is happening here on a high level is that we for each Verilog variable allocate a register, and then for each register we need to build a next state netlist, such that we know how to update them each clock cycle. And this is probably easiest seen with the concrete example. So in Verilog we have 2 different kinds of assignments, non-blocking and blocking assignments. So we keep track of these using 2 maps, sigma and sigma non-blocking. And now we need to create a netlist for this Verilog code. So compiling the first line is quite straightforward because the right-hand side is simple. We do not need to add any new cells, we can simply update the sigma map, saying that A is now free. But for the second line, the right-hand side is a little more involved. So here we need to generate a few new cells, addition cells, and then we set the sigma for B to one of the outputs of these new cells. And here, after everything is done here, we have a netlist and we can read out how to update the registers using the sigma maps. Another important pass in Lutsig is Lutzig's X-value optimization pass, so let's look into that pass. So in synthesis, X-values is a way for hardware designers to signal don't care. Consider for example this Verilog code to the left here. So here we have an if statement with one branch assigning 3 to A and the other branch assigning X to A. And here the X value is a way for the hardware designer to signal to the compiler that the compiler can insert any value here. And this of course opens up optimization opportunities for the compiler. because if we say that x should be equal to 3 here, then the compiler can replace this whole if statement with an assignment to a, saying that a should always be equal to 3, and this allows us to compile the if statement without generating any maxes, and so on. But one problem is that the Verilog standard x semantics is not a good fit for synthesis. So instead of following the standard here, we had to come up with our own semantics for x values, and our semantics is based on streams of non-deterministic bits. And not only is this pass an optimization pass, this pass is actually required to be able to do technology mapping later, because our target cell set do not include any non-deterministic cells, and after this pass, our netlist is entirely deterministic. And Lutsig also does technology mapping, so let's look into that as well. And technology mapping in Lutsig is carried out in two passes, so let's look into the first pass first. By technology mapping, we mean that we have a netlist implemented in terms of abstract gates, and we want to produce an equivalent netlist implemented in terms of the cells natively available in our target technology, in our case FPGAs. So, when targeting FPGAs, we could in theory map all cells to lookup tables, so-called LUTs. But it's better to exploit the special purpose hardware resources available to us, such as, for example, carry chains. And this is exactly the responsibility of the technology mapper for high-level cells. The mapper takes high-level cells, such as addition or equality checking, and maps them to the special purpose hardware resources available in FPGAs. And after the first technology mapper is done, a second technology mapper is run to map all the cells not already mapped by the first mapper. So let's look into that mapper also. And the second technology mapper is based on graph coverings in the following sense. So the first step is to find a covering of our input netlist, for example something like this. And then each cover is turned into a lookup table or LUT. So this gives us our technology mapped netlist. But now we need to take into consideration that this pass differs from the other passes in Lutsig, because this pass is not verified. This pass is instead based on translation validation, because running a graph covering algorithm is computationally expensive, and translation validation allows us to run the algorithm outside our logic. It also allows us to use existing mappers. However, for this first version of Lutsig, we found it easier to build our own mapper than integrating an existing one. Anyhow, to prove the input and output netlist equivalent, we first break down the equivalence problem into a series of small Boolean problems that can be solved by SAT solving, and then, using all-for automation, we glue the result returned from the SAT solver back to one big equivalence claim for the two netlists. And thanks to the infrastructure available in Hall4 for SAT solving, we do not need to add the SAT solver used to our TCB, because the Hall4 infrastructure can create a Hall proof from the SAT proof. Okay, so let's wrap up. So, of course, in the paper you will find more details about everything that has been mentioned in this talk. And in particular, you will find two case studies. One case study about how to verify a simple moving average filter, showing how to use Lutsig in practice, and there you will see how we, for example, encode circuits in Hall, etc. And since Verilog is a popular language, you can connect up Lutsig to other Verilog-based tools. So, we for example show that we are able to compile the Verilog output of the verified high-level synthesizer Vericert using Lutsig in the paper. All in all, Lutsig is a verified Verilog compiler that compiles Verilog designs to netlists and does technology mapping for FPGAs. By verified, we mean that Lutsig is proved semantics preserving, and this enables us to transport properties proved at the Verilog level down to the netlist level.